right, everybody, let's go ahead and start today's lesson, the last part of section 5.2, simplifying variable expressions. All right, let's get right into it. So what we want to do is we want to reduce these expressions the best that we can as far as possible. And to do that, what we want to do is treat them like we did with square roots. So let's take this radical and let's break it into whatever is a perfect cube root and then whatever is not a perfect cube root. Let's start with the number 64. So when you got the number 64, you got to start thinking to yourself, all right, are there cube roots? Is 64 a perfect cube root, first of all? And you know what? It is. 4 times 4 times 4 is 64. So what I'm going to do is I'm going to transfer the number 64 over here because I can find its cube root. The next thing is, let's go to the variable. Now, y to the 6th power is a cube root. Now, do you remember that this y to the 6th power could be written like this with the root? Now, the question is 6 divided by or divisible by 3? And it is, right? That means that y to the 6th is a perfect cube root. That means there is nothing over here that is not a perfect cube root. So we can actually just do this problem. So the cube root of 64 is 4. And the cube root of y to the 6th is 6 divided by 3, which is y squared. Now think about that. 4y squared times 4y squared times 4y squared. Yeah, that does work, right? That's 64. Add up all your exponents. That's y to the 6th. So there's your answer. Okay? Let's go ahead and go into part B and see if we can make any sense out of that. So I would think a good idea would be to rewrite this as two different radicals. Like the 4th root of x to the 4th over the 4th root of y to the 8th. Now, once again, you know what might even be a better idea? Maybe rewrite this as fractional exponents and see if these are perfect roots, because I think they are. This one is x to the 4 divided by 4, and that's something we can do. This is y to the 8/4. So I think we have an answer here, everybody. That's x to the 1st power, which, heck, we could just write that as x, right? And then down here, that's y to the 8 divided by 4 is 2. Oh, that problem's done right there. All right, let's move on. Let's try these as well. Okay, these are going to get more difficult, but we'll do the best that we can. All right, so let's break this into 5th roots. Perfect 5th roots, and then non-perfect 5th roots. Okay, let's start with the number 4. Can 4, does it have a 5th root? And the answer is no, it's too small. There's nothing there that would work. How about a to the 8th? Okay, so what you got to do is you got to start thinking about this. So you got a 5th root. What is the biggest multiple of 5 that fits into 8? Just a to the 5th. And this would have to be a to the 3rd, because 5 plus 3 is 8. Let's go with the b's. I'm going to go with, there's a 14 here, so I'm going to go with b to the 10th, because 5 divides into 10, and b to the 4th here. And then finally, c to the 5th is a perfect root. So I'm ready to write my answer. So what I'm going to do is think about all of these terms inside of here as fractional exponents. What's 5 divided by 5? A to the 1st. What's 10 divided by 5? B to the 2nd. 5 divided by 5? C. And all this over here is a non-perfect root, so it needs to stay as is. And there's our answer. That's the best we can do. Let's go to part B. Okay, we got a problem here. That expression has a radical in the denominator, and y to the 8 is not a perfect cube root. So we really should rationalize this. So I'm going to go ahead and show you what I would do. I'm going to multiply it by 1. So I don't change the value of the expression. But what I mean by that is I'm going to multiply by a perfect cubed root. All right, now watch what I do. So I'm thinking about this y to the 8. What number, it has to be a little bit bigger than that, is a multiple of 3? And that's 9, right? So if I put y to the first, or just y right there, and y here, I think this is going to work. So watch what I get here. Up top, it's x times cube root of y. On the bottom, I can multiply these together. Remember, that's an exponent of 1. Cube root of y to the 9th power. Now the numerator stays the same. My denominator, 9 is divisible by 3. Done. All right. We think about with this expression here. I think we should simplify this as much as we possibly can. So I think I'm going to write a fraction. I'm going to go through this very carefully. Okay, now I'm going to look at my numbers. 14 and 2. Isn't that 7? It is. Now I'm going to look at my x's. It's a 1 and a 3/4. Now remember, when you divide, you actually subtract your exponents. So 1 minus 3/4, it'd be 1/4. So that'd be x to the 1/4. Let's go to the y's. So there's only one y. It's y to the 1/3. And now let's look at the z's. Okay, do you see that negative exponent? Now remember, that is a reciprocal, so it becomes z to the 6 up top. And I guess there's a 1 left over down below. So you don't really need that 1. The answer to this problem is this. Those terms could be written as radicals too, if you wanted to. All right, let's go on to the next problem. What if we're adding and subtracting? Well, it's all about like terms. So in part A, what I see here is that I've got like terms. So 5 plus 6 is just 11 times the square root of y, as long as you have like terms. Part B, we don't have like terms, but maybe we will. So what I want to do is I want to rewrite each expression, because what I see is I have cubed roots. If I can get the same cube root, I can probably do a little work with this. So let's take this first expression. I'm going to rewrite it as 12 times some cube roots, and I'm going to see if I can come up with some perfect cube roots. So first of all, the number 2, it's too small to be a cube root, but z to the 5th, I can make it z cubed times z squared. 3 and 2 makes 5. And the key is that z cubed is a perfect cube root. Now the next expression, I'm going to do the same thing. 54. 54 is not a perfect cube, but 27 times 2 will work. And z squared is too small to be a perfect cube root. So now, here I go. I'm going to work on this information. So this, I'm going to leave as is. This, 3 divided by 3 is 1, so that's just z. And then this is not a perfect cube, so I'm just going to write cube root of 2z squared. Now I'm going to keep going. Minus z. This right here I know what the cube root of 27 is. It's 3. So I guess what I can do is I can just move this over a little bit and make this a 3z. And then finally, look at this. I've got the same term there, times the cube root of 2z squared. So I actually have two terms that are identical, and I can now just subtract that. 12z minus 3z is 9z times the cube root of 2z squared. So it's all about creating like terms. Okay, let's do a little bit more work on this and see what we've learned.